Am I centered in frame and all?
Yeah, you're good.
Okay.
All right. Hello, everyone. Thank you for joining us today at our live session. We are going to get to a whole bunch of questions today. Super excited. And I'm going to hand this over to Chris and let you welcome everybody.
Okay, it's good to have everyone online and by email. Looking forward to answering your questions about astronomy for the online course, starting right now.
Thanks, Chris. The first question is from Hamid, who left a question. I don't know if he's on with us live right now, but put a question in the chat that says, how do astronomers calculate that the moon is moving away from the Earth at a rate of 1.5 inches per year? How far in the past can we extrapolate this? And would that rate be faster or slower in the past?
Yeah, good question, one I haven't had before. Well, we know this because of, unless you're one of the 1 in 12 Americans who don't believe we actually went to the moon, we know this because we did go to the moon. And among the things that got left behind on the moon, apart from rovers and the landing pad of the lunar module, were various geological and magnetic experiments that many of them have continued to function without interruption for 50 years. So the simplest of these experiments are simple reflectors, corner cube reflectors that can be used to reflect laser light off the moon. And so we use essentially laser ranging to measure the distance to the moon with very high precision, to level of a millimeter or so. And so it's fairly trivial to show that the moon is getting, on average, further from the Earth every year by that amount, 4 centimeters, 1.5 inches. And it's not very much. It's amazing that we can measure it, and we can only measure it because we left something behind on the moon that lets us do a scientific experiment with laser light. The reason why the moon is changing its distance from the Earth is because in the gravitational interaction between the Earth and the moon, there's the nature of that interaction is sort of akin to a weak form of tidal locking, where there is angular momentum and energy transferred between the Earth and the moon as a bound system. The total amount of energy and angular momentum, of course, is unaltered. That's the law of physics. But what it means is that as the moon gains gravitational energy, potential energy from the Earth, it moves to a slightly larger distance, and the Earth's spin rate, of course, therefore slightly slows down. So the Earth's day is getting about 1/millionth of a second longer a year, and that's part of the same physics. So we know this rate currently. Now, of course, we then have to extrapolate to say what this rate would have been in the past, but it does suggest, if you play it back 1 billion years, that the moon would have loomed substantially larger in the sky than it does now, also meaning that the perfect juxtaposition of 1/2 degree subtended in the sky of the Earth, of the sun, and the moon, causing total solar eclipse phenomena and lunar eclipse phenomena, that wouldn't have pertained in the past because the moon would have been much bigger, a bigger angle. If we play that forward, and this is all sensible with the idea that the moon formed by being splashed off the Earth of a giant impact of a Mars-type impactor very early in the Earth's history. And if we play this forward, it will continue. The Earth and the moon will continue to increase their distance, and it is indeed possible sometime in the far future, tens of billions of years from now, that the moon will escape the Earth's gravity and be captured or disturbed by other objects in the solar system and leave our realm of gravity. But it's a pretty cool thing that we can measure such a tiny effect because of the moon astronauts going there 60 years ago. Ready for the next question?
Thanks, Chris. The next question is from Ilsa Martin, who is on with us live, who asks, what is all the fuss about discovering a unified theory of forces? If gravity is different, why is that not okay?
In a sense, it is okay at the moment because we have a very good theory of gravity. General relativity is now just over 100 years old, pretty much just celebrated the centenary of its testing. The theory was published in 1916 and tested in 1919. And it's passed every test with flying colors, including more recent tests involving gravitational waves and black hole mergers and the event horizon of the black hole that we saw this year and so on. So it's a very successful theory, and it stands on its own merits to describe how objects behave and how mass attracts other mass in space. We equally have very successful theories of microscopic matter. The so-called standard model of particle physics has a number of parameters that's uncomfortably large for people who want efficiency in an elegant theory. But this theory describes how subatomic particles and atoms and the nuclei of atoms work extremely well. So we have these successful theories of particles and of gravity. Yet it is an agenda of physics to continue to simplify theories of nature. The motivation for the unification is that we've already shown that some of the four fundamental forces can merge at sufficiently high energy. In the 1970s, several Nobel Prizes were awarded at CERN and other accelerators for demonstrating the electro-weak merger, which is that at sufficient energies or temperatures, and that would have pertained in the early universe, the electromagnetic force responsible for light and the weak nuclear force responsible for the fact that heavy atoms decay can be unified into one force. That was a very powerful insight from the 1970s. And so it's natural to then wonder whether that electroweak force might indeed be unified with the strong nuclear force, and then with the much weaker force of gravity. The unification with a strong force, so-called supersymmetry or grand unified theories, that's not completely successful yet. It's not been tested. It's difficult to test with accelerators. And the unification with gravity is extremely difficult because of the very, very different strengths of these nuclear forces and the weak force of gravity. So we're not really in a position to come up with such a unified theory. People talk about string theory and various other things, but this is pretty speculative. There are no experimental tests. But the basis for looking for this unification is the fact that our theories are sort of a patchwork quilt, where each theory applies in its own energy range, energy domain, and not across energy domains. And physicists really are pretty confident that at some level there must be a fundamental theory of all the four forces. Ready for the next question?
All right, the next question is from Jacqueline Joan, who sent an email asking if you have any ideas or have ever seen anybody represent invisible objects like gravity wells in classroom models or wire models of the solar system in schools. She's interested in things like invisible planets, like Planet 9, or if a gravity well, like a black hole, were to move through our solar system, and being able to represent that. So, do you have any ideas for how that can be done, or have you ever seen it done?
I mean, definitely some planetarium science centers use the sort of rubber sheet analogy for gravity and mass bending space-time to set up a situation. I mean, you can make a curved, rubber doesn't really work for this. You sort of need curved or shaped plastic. But I've seen situations where people use curved plastic surfaces and roll marbles or small balls across the surfaces and show how they deviate according to the gravity, and the bending of the surface is proportional to the mass on that surface. So that kind of model is used fairly successfully in science centers and planetaria. Representing invisible objects otherwise, and especially in 3 dimensions, like with a wire grid, that also has been done. I've seen a couple of museum, multimedia type museum exhibits that try and represent a grid of space, essentially a 3-dimensional grid, like as in wire mesh, but in 3 dimensions, and look at the distortions of that wire grid according to objects that sit in that space. So that can be done in 3 dimensions. It's substantially harder. So these are actually not easy things to do in a typical classroom. They have to have significant construction and quite a high degree of craftsmanship to execute. But if you search for models of curved space-time or solar system models, scale models of solar system are fairly standard thing, but I'm pretty sure you're not asking about that. You could find some of these online, and some of them are not too difficult or expensive to replicate. Ready for the next question?
All right, thanks, Chris. The next question is from Daily Artonaut, who's on with us live, who would like to know if there will be other question and answer sessions this year. It's so great to be able to have such a valuable resource while completing this online course. And the answer is yes, but I'll let you talk about the frequency.
Sure. I mean, I have had some travel. I don't have any more travel the rest of the year. And when I'm not traveling, we try and keep a cadence of once every 2 weeks when I'm traveling, or if other things intervene, deadlines for proposals and various things that we have to juggle in our group. It can stretch to 3 weeks, I guess even longer occasionally in the summer. So the short answer is we plan to do this every 2 weeks through the end of the year. Ready for the next question.
Okay, the next question is from Pecornin, who's on with us live, who asks, why is there a black hole at the center of all galaxies? So I guess the question really should be, is there a black hole at the center of all galaxies? And if so, why?
Right. So it was a surprise, and it wasn't an overnight discovery or a sudden surprise, but it was a gradual realization of astronomers through the late 70s and mostly into the 1980s that every galaxy had a black hole. Evidence was starting to accumulate in the late 70s and was strong by the mid 80s that our own galaxy had a black hole of about 4 million times the mass of the sun. Measuring black holes in other galaxies is much harder because those galaxies are hundreds of times further away than the center of our galaxy. And so the Hubble Space Telescope and its spectrographs were used for this work in the 1980s. And over time, these spectrographs were able to show that there was dark mass causing very high stellar velocities in the center of other galaxies. And as time went by and the limits of detection of these black holes improved, it became clear that every galaxy that we could inspect in the nearby universe, by which I mean distances of tens of millions of light years, including Andromeda, the nearest neighbor, has a black hole. Now, sometimes for a very small mass galaxy, say Andromeda's neighbor M33, which is nearby but very low mass, the sensitivity of these experiments is not enough to detect the black hole. So there are actually some nearby galaxies where no black hole is detected, but there are small galaxies where the linear relationship between black hole mass and old stellar mass in a galaxy suggests that they're just too small for us to detect. So to be formally correct, we do not detect a black hole in every galaxy because some galaxies are either too small and the black hole is too small for us to detect based on predicted properties, or they're too far away and the sensitivity isn't good enough to detect them to isolate the center of the galaxy. So with that caveat, every galaxy we've inspected has a black hole, and they tend to be dark. They tend to be inactive. They're not fueling, chewing up stars and gas and spitting out large amounts of energy. So that realization of every galaxy having a black hole really happened over a decade or 1.5 decades. It didn't happen overnight, but it's holding as more data comes in. The why question also makes sense. The center of a galaxy is the densest part of a galaxy. It has the largest concentration of gas and dust and stars. And in the stellar pileup at the center of a galaxy, normal gravitational processes can actually cause the central star cluster to turn into a cusp, to really rapidly collapse into something that will fit the formal definition of a black hole. And now we've done this in a computer. If you simulate the central regions of galaxies and the star clusters they contain, then in natural evolution, eventually a black hole will form. We think the seed black holes of galaxies formed very early, as the galaxies formed billions of years ago, and they were small, maybe hundreds or a few thousand times the mass of the sun. And then over billions of years, these black holes have grown to medium mass, like our own galaxy, a few million times the mass of the sun, or the biggest ones, a few billion times the mass of the sun, like M87, the black hole we imaged earlier this year. Ready for the next question.
The next question is from Christine, who sent an email asking, for the initially discovered hot Jupiters, why hasn't their gas evaporated after having migrated so close to the star?
That's a good question, and in fact, their gas is slowly evaporating. That process is, the physics of that is called ablation, where strong radiation will gradually essentially evaporate gas from an object, basically because they make the temperature of the gas so high that the average motion of the molecules exceeds the escape velocity of the planet. That's what's actually happening when a giant planet close to a hot star loses its atmosphere. But this is a very slow process. So these Jupiters, when we say they're close to their star, they are indeed close. I mean, they're much closer than Mercury is to the Sun. But they're not so close that the atmosphere of what is really quite a massive planet, much more massive, hundreds of times more massive than the Earth, is going to be lost at a very high rate. Eventually, if you play this forward, they will lose most of their atmosphere. And in fact, the gravitational coupling between the hot Jupiter and the star, which tidally locks it with one face always pointing in the same direction towards a star, there will be gradual secular evolution such that the planet will spiral into the star and be lost in the star. And that could actually happen before it loses its atmosphere. Ready for the next question?
The next question is from Lawrence K., who is on with us live, who asks, if a particle approaching a black hole accelerates to the speed of light, does it ever actually reach the event horizon on account of time dilation?
It's interesting. As seen from the outside, no. So whether it's a subatomic particle or a spaceship or a physical object of intermediate size, as that object falls towards a black hole, it will, of course, be accelerated by the gravity of the black hole. In most cases, objects that are moving fairly slowly, tens of kilometers per second or hundreds of kilometers per second, falling into a black hole will not reach the speed of light. They will be accelerated but not get to relativistic speeds. But let's say they do. Let's say they get to a significant fraction of the speed of light. Then in practical terms, those objects will fall into the black hole. They'll pass the event horizon, and that information and their state will be lost to us forever. As seen from the outside, however, the time dilation takes place because the light from that object coming back to us struggles to, you can think of it sort of losing energy by struggling against the gravity of the black hole. And that loss of energy corresponds to a redshift. That's the radiation wavelength. But a concomitant of that effect is the dilation of time. And so in the clock that might be held by an object falling in, a single particle doesn't have a clock, then that clock would seem to slow down, and it would, in practice, take the particle forever to reach the event horizon, and it would lose all of its energy that it sent back to us in terms of reflected light as it reached the event horizon. We've never tested this idea, but this is what general relativity says will happen. Ready for the next question.
All right, our next question is from Andronash Adriana Valentina, who asks, how do you see the future of space resource explorations and manufacturing stuff in space, for example, 3D printing? Do you think there's a future in any of that?
There's definitely a future. In fact, there's a present in that. NASA, the agency that's not always considered very visionary, they've jumped on board some technology development, and they're partnering with small startups and companies, mostly in California, to prototype technologies that will help us live in space, that will help us go in space, and I mean now far beyond the low Earth orbit of the space station. And 3D printing is an important part of that. So the 3D printing technologies have matured very rapidly, and the price of printers has come down. NASA's experimented with very sophisticated 3D printers, and they've had those on board the space station, I think, now for a couple of years, different kinds, as a way of making components in space. So if you want to construct something complicated in space, it's expensive and takes a lot of energy and rocket fuel to lug stuff up out of Earth's gravity. It's easier if you can find the raw material out in space, and for instance, the moon should be a good source of raw material, to do the manufacturing in Earth orbit. And so that's been tested. And so I think eventually when we start to construct habitats, maybe on the moon, maybe on Mars, when we eventually start to travel in the solar system and have off-Earth outposts that are further away than the space station is, 3D printing will be a big part of this. And so it's pretty mature technology now, and other countries apart from the US are experimenting with it too. It's going to be a major part of how we are able to live off Earth. Ready for the next question.
All right, the next question is from Simon, who is on with us live. I have heard people describe information as if it is some kind of core particle. How can actual matter consist of nothing but information, and what does that mean?
Yeah, the word information is used sometimes a bit loosely in talking about science and scientific issues. Information in computer science or in physics, has a quite particular meaning. So we can imagine information in general as describing physical states. How many bits of information does it take to describe a physical state? And by bit of information, I mean a very simple binary digit like on, off, yes, no, hot, cold, loud, soft, so on. So it's the simplest categorization of a state. The simplest analogy to make it obvious is the spin of a particle. So a particle can, as seen by the observer, can either be spinning one way or the other, and it's essentially a binary thing. So there's one bit of information attached to the spin of a particle. There's also one bit of information attached to the fundamental nature of a particle, where it could have the opposite set of quantum properties and be an antiparticle. So you could say there's one bit of information attached to whether some small entity that you're dealing with is a particle or an antiparticle. So that's an example of the way you can have a set of bits of information that might describe the nature, the physical state, the properties of a subatomic particle. And then when you have a lot of subatomic particles, you're just multiplying out that amount of information. So information does make sense in terms of talking about fundamental particles, and then if it makes sense for them, it obviously makes sense for aggregates of those particles. Ready for the next question.
All right, the next question is from Arnav, who's on with us live, who would like to know how we calculate the density of a planet. And I'm going to speculate that it's either exoplanets or planets in our solar system, but maybe you can talk about both.
Right. Yeah, so in our solar system, we have space probes. So we've obviously visited all the major planets. So Pluto just got a fast flyby because the speed and energy required to get that far out in the solar system meant that it couldn't slow down and go into orbit. So maybe take Pluto out of this comparison. But for the other planets, there have been slow flybys or probes that go into orbit for extended periods around them, like Cassini did around Saturn. And in that case, we can use the telemetry and the orbit of the satellite itself as a probe of the planet that it's orbiting. And that orbital data gives a very good measure of the average density of the planet and the mass of the planet. And since you can see the atmosphere and the size of the planet, you can therefore calculate the mean density. And if you have some idea of the structure of the planet, you can understand the density of the various components, like a thin, low-density gas surrounding a rocky material or maybe an iron core. So those are measurements that have been done in the past, and of course they've led to the inference decades ago that each of the gas giant planets has a rocky core, even though we can't see that. And these rocky cores, they're a little uncertain in mass because they're a small fraction of the mass of the gas giants, but they are probably in the range of 3 to 6 or 7 times the Earth's mass in each of the giant planets in our solar system. Now, when it comes to exoplanets, it's a slightly less direct process because we don't have space probes there. So we're not using the gravity and the behavior of an orbiting test particle like a space probe. In the case of exoplanets, we're gathering 2 pieces of information. So of the 4,000 plus exoplanets, the majority of those have been measured by the transit or eclipse method that Kepler satellite uses. And that gives the size of the planet because it says how much the star is dimmed when the planet crosses in front of the star. Separately, we have the Doppler method, which measures the mass of an exoplanet. And we now have several hundred cases where both methods can be used on the same exoplanet. And that's important because one method, the Doppler method, gives you mass. The other method, the transit method, gives you size. And if you have size and mass, you've got mean density. And so that's how we know the mean density of several hundred exoplanets. Now, mean density is tricky because it doesn't really tell you the full state of the planet, since we know the planets may well have rocky cores, or iron cores, metallic cores, and then rocky or lighter rock outer parts, and then very light gaseous atmospheres of different kinds of gases. No single parameter like mean density can tell you the structure of an exoplanet, and so we have to make models and assumptions. But that mean density is a very important step along the road to really understanding the nature of exoplanets as worlds in their own right, as opposed to just dots in the sky. Ready for the next question?
All right, thank you, Chris. Excuse me. The next question is from, the next question is from Wendy Graham, who sent an email asking if a solar system is ejected far out of its galaxy during an interaction or merger of two galaxies, what would happen to it? Have we ever observed isolated solar systems like this? Is there a dependency of a solar system on its home galaxy?
No, we've never observed a solar system, which is to say a star and its attendant planets, flung out of a galaxy because of an interaction. But simulations suggest that it must happen. It's probably quite rare, though. The Milky Way, of course, has formed over billions of years by mergers with mostly smaller galaxies, and some of those interactions probably ejected planets, stars around, and the planets around them. So this has happened in the Milky Way. When Andromeda and the Milky Way merge in about 3 billion years, also because they're two pretty massive galaxies and it's a direct collision, more or less, this will happen dramatically, including perhaps to our solar system. So this could be a fate that awaits us as well. But it's so difficult to detect an intergalactic star, a single intergalactic star. There are several claimed detections of intergalactic stars, but they're of course very far away, tens of thousands, if not hundreds of thousands of light years. So there's no possible way to detect planets around those intergalactic stars. And even the number of intergalactic stars relative to the number of stars captive in the galaxy is not very well determined. It's predicted by theory, but it has a wide range. So this is one of the challenge goals of astronomy with large telescopes, is to actually detect intergalactic stars and try and tell the story of how and why and when they were ejected. Ready for the next question?
Thank you, Chris. The next question is from Michelle, who sent an email. And she would like to know, what is the current state of the ozone layer? We used to hear a lot about it. Is there any update on it? And is there any relation to this to climate change?
Yeah, the ozone hole has actually been in the news this past week, in fact. So NASA's been monitoring the ozone hole. There are orbiting satellites that can detect ozone. Ozone is, of course, O3. It's a sort of hybrid. It's a relative of molecular oxygen that forms 20% of our atmosphere. Ozone is a trace ingredient, very important ingredient because it's highly absorbing of UV radiation, and so it performs as a shield. So the ozone hole was first detected, I think, in the 70s, maybe even in the 60s. And it came and went. It had a seasonal variation and probably a cyclic variation with the solar cycle as well. The good news is that there was a human impact on the ozone hole, making it worse through the modern industrial age, where chlorofluorocarbons, which are typically, not exclusively, but they're gases that are most familiar to us from cooling systems or refrigerators, but also used in industrial processes. When they're leached out, when old refrigerators are destroyed or in landfills or broken, their chlorofluorocarbon molecules go into the atmosphere, and industrial processes do the same thing. And these molecules essentially interact with ozone and remove ozone. So we had this ozone hole, this lack of this protective ozone layer, and the hole was biggest at the poles for other natural reasons. So this got worse for some decades, and it led to some, serious concern among scientists, because we were obviously contaminating the atmosphere with these kind of strange chemical pollutants that interacted with ozone. That process reversed because policy in major industrialized countries really started to rule out the use of those particular compounds in refrigeration and other industrial processes. People were able to find substitutes that didn't have this effect. And so we sort of turned the corner, and the ozone hole started shrinking and getting less profound, and we looked like we were losing less ozone, and recent observations have confirmed that we really turned the corner on this. So this was a danger really averted by fairly prompt action and by legislation, by policy, actually. So that's one of the few good stories in the age when we seem to be messing up our environment on a global scale. Here was one situation where we were causing damage and we reversed the damage. Ready for the next question.
There is a follow-up question from one of our first question about the moon, and Space-Time with Robert would like to know, will the moon leave us before the sun consumes the Earth? What's the time scale on both of those?
Yeah, I think not. What I've read about the extrapolation of the moon's migration away from the Earth is that it's many billions of years. The Earth being, well, first of all, the biosphere will be torched probably in about a half to 2/3 of 1 billion years from now, as the sun uses its fuel as hydrogen turning into helium and reconfigures and runs a little hotter. So the sun is going to gradually get hotter as it evolves, even while it's still fusing hydrogen into helium. And that will create a situation where the oceans boil and the biosphere is pretty much toasted in less than 1 billion years. So that's well before the sun runs out of fuel, goes red giant, and engulfs us in its outer envelope. And the moon migrating away from the Earth will happen on an even longer time scale. The sun's conversion into a red giant, with a gaseous envelope that engulfs the Earth and actually goes out to about the distance of Mars, that's unlikely to physically affect the moon-Earth orbital enough to dislodge the moon, because it's essentially just weak radiation. It's not pushing hard enough against the moon to loosen the grip the Earth has on the moon. So we won't see the moon leave the Earth before the sun dies, basically. Ready for the next question.
All right, thank you, Chris. The next question is from Gitanjali, who sent an email asking, how do astronomers measure the size and age of stars in faraway galaxies?
They don't really measure the size of stars in distant galaxies because stars are so small that we can't resolve them except really in the nearby universe. So stars like the sun, or slightly larger than the sun, are 1 million or so kilometers in diameter. And the nearest stars are a few light years away, and the light year is 6 trillion miles or 10 trillion kilometers. So you're talking about an object that's a few millions of kilometers across at a distance of tens of trillions of kilometers. And that ratio, of course, is 1 million or so. So these are super small angles to try and resolve a star. And we can only do it for the nearest stars or the largest stars like red giants or supergiants. So no chance of measuring the size of stars or seeing their size in a distant galaxy, even in a nearby, even in a fairly nearby galaxy. It's just too hard. The age of stars, however, we can measure, and we don't measure it individually, we measure it in the aggregate. So we use the fact that galaxies have stellar populations, like the young and bluish stars we see around us in the spiral arms of the Milky Way, relative to the somewhat older, more polluted with heavy element stars we see in the bulge of the galaxy, relative to the low heavy element abundance and very old stars we see in the halo of our galaxy, 3 different populations. And we can isolate those same populations in distant galaxies. Even if we can't see individual stars, we can see these aggregate populations. And by measuring the colors and the spectra of the aggregate of these stars, again, it's spectra of millions and millions of stars in one go, not individual stars, then we can make a model for how that population came to be. And so people have a fairly good measure of the age of stars in distant galaxies. It's not super precise. Maybe at the 10% level we can say, like, this galaxy has stars that are 9 or 10 or 11 billion years old, and this galaxy or this population is much younger and much bluer and has more heavy elements, and so is about 1 billion years or so. So these methods are fairly reliable, and they're calibrated, of course, by careful study of populations of stars in our own galaxy much closer. Ready for the next question.
The next question comes from Brandon Kelly, who's on with us live, who says, I remember the big deal of the discovery of the Higgs boson, or the God particle. Has anything useful come out of this discovery, or any more progress been made?
Very little. It's been a disappointment to physicists that so little has been learned since 2012, 2013, when the Higgs was detected at the Large Hadron Collider in Geneva, Switzerland. So that discovery was the culmination, if you like, of the Standard Model of particle physics, because with the suite of particles and the 3 generations of quarks and light particles that we see in particle physics, this was the object or the field, if you like, that created the mass of those particles, that ascribes mass, the mechanism for mass. And so it was a culmination of the Standard Model of particle physics. And it came in at a mass measured in energy units, as physicists do, about 120 to 130 giga-electron volts. Not a surprising number. However, physicists have been very disappointed by the thin pickings, the slim pickings from CERN since then. That's 5 or 6 years and one upgrade of energy. Since then, they've been hoping to see more physics from other particles, even hints of supersymmetry, hints of unification, relative to a question was asked earlier in the session, in the Large Hadron Collider, and they've really seen very little. There are some little interesting exotic bits of particle physics, but nothing profound that might have been expected post-Higgs discovery. And so they've sort of retreated into a view of trying to measure as much as they can about the Higgs itself. And what that means is the Higgs has various modes of production. There are mechanisms by which the Higgs manifests interactions with other particles. And so there's a complex tree of interactions that can lead to Higgs particles. And so just by piling up events and collisions, they're hoping to see all the possible pathways by which the Higgs can be created. There's a standard bottom quark, bottom anti-quark interaction that leads to 2/3 or most of the Higgs production. But there are other smaller channels. And I think in the details of how the Higgs can be created and all the different ways it could be created, there may be some new physics, there may be something exciting. But the truth is, it's been disappointing. And this is when physicists in Europe are really getting together to pitch an even larger, even more powerful telescope with a, eye-watering price tag of probably close to 100 billion euros. And it's going to be a hard sell when there's so little come out of the Large Hadron Collider after the Higgs. Not to denigrate the Higgs discovery, it was a pretty momentous discovery in physics. Ready for the next question?
All right, the next question is from Vasilis, who's on with us live, who asks, what causes a star like Altair to rotate so rapidly that it becomes oblate?
Well, stars can rotate rapidly for 2 reasons. The most typical reason is its initial conditions. The rotation of a star reflects the angular momentum of the gas cloud that formed the star, because the stars don't form typically singly, so there's one large cloud that fragments and individual subregions collapse by almost direct gravitational infall. They have some angular momentum. That angular momentum is amplified as the star forms until you have a spinning star. Sometimes that spin is slowed down in the early phase of the star as the star encounters drag with its surrounding region of gas or interactions with nearby stars. A star like Altair that is rotating really rapidly, that's inferred to be part of its initial conditions. There's variation in the angular momentum of diffuse gas clouds that can form stars, and so not all stars will form with the same angular momentum and have the same spin rate. So the sun is oblate, and pretty much every star that has rotation is oblate in that sense of being bulged out of the equator because of its angular momentum. Altair is just a slightly more extreme example, but it's not so extreme that it suggests some strange mechanism. I said there was a second mechanism that can contribute to the spin rate and angular momentum of a star, and that's, of course, interactions with other stars. So if early in the star's history, the star forms in a tight cluster and there are star-star interactions, that obviously can affect the angular momentum. We don't think, for example, that that happened to the sun. The sun likely formed in a fairly isolated situation. Ready for the next question?
The next question is from Talal, who is on with us live, who would like to know, how has the cosmic microwave background falsified speculations of a homogeneous universe?
Well, the microwave background has structure in it. If the universe were truly homogeneous, and homogeneous in physics means sort of the same in all locations, on average. And the universe is homogeneous on average in the sense that we think roughly the same populations of galaxies and the same background radiation are seen in different regions. But the universe, of course, is not truly homogeneous, and that's imprinted in the microwave background. That wasn't clear in the first detection by Penzias and Wilson in 1964, and it was barely clear when COBE was launched in the late 1980s. But by the time we get to the current generation of microwave satellites of WMAP and the European Planck mission, they have exquisite precision, and so they can clearly show that the microwaves are not homogeneous. They have variations that are about 1 part in 10 to the 5 or 1,000th of a percent, variations in temperature or intensity, whichever way you want to think about it. And those small speckles or ripples or inhomogeneities in the microwave background reflect the very early universe, and they're essentially the seeds for the subsequent formation of galaxies. So the fact that the universe is not homogeneous and that the early universe was not homogeneous means that we can sort of trace the initial fluctuations that eventually grew like little acorns growing into oak trees into the big galaxies we see. Now, the other issue of the inhomogeneities is where do they come from? Because when the microwave background, we're looking back at the universe when it was 1,000 times smaller than it is now, 1,000 times hotter, 1 billion times denser. It's quite a different place. These inhomogeneities in the inflationary cosmology reflect quantum fluctuations that were amplified by inflation to the size, essentially, of galaxies, or the seeds for galaxies. Quite an extraordinary supposition. Ready for the next question.
Next question is from Christine, who sent an email asking, would it be realistically possible to plant sufficient vegetation on a planet like Mars, where plants can feed off the CO2 in the Martian atmosphere and release oxygen? And would oxygen stay in the Martian atmosphere? And for that matter, what about Venus?
Right. So the habitability of Mars, or the viability of growing food on Mars, I mean, more people saw the movie The Martian than read the book. The book had a lot more scientific detail, and he was written by a space scientist who worked at NASA for many years. And so it's quite plausible. So these are not going to be crops, however, that grow out in the open on Mars, because the truth is the atmosphere is about 1% of the pressure of the Earth atmosphere. So that's just too thin. We have photosynthetic organisms and organisms that can survive quite well harvesting the oxygen in the Earth's atmosphere and respirating with it. But in 1% of that pressure, you really have a hard job making any kind of plant work. And so the habitats where Mars can grow food and plants and crops are going to be self-contained habitats, just bubble domes, which create more like Earth conditions. To get to the point where the raw Mars surface, blasted by UV radiation with a very thin atmosphere, could actually support microbes, is not clear that that can happen. So microbiologists have speculated about extremophiles, so extreme microbes, the kind of which we have on Earth, that can handle very exceptionally adverse conditions. It's just within the realm of possibility, especially with genetically engineered extremophiles from the Earth, that they could get a hold on the Martian surface and start to do the job of converting carbon dioxide into oxygen and generating an oxygen atmosphere. It would be an incredibly slow process, because these extremophiles are still struggling in that thin atmosphere to do their work. And you're talking about transforming an entire planet, smaller than the Earth, but still substantial size. So that's an incredibly slow way to terraform Mars or turn Mars into a habitable world. The mechanism just about works, but it's awfully inefficient. So I think Mars is not going to be made livable on its surface by that mechanism. Ready for the next question?
All right. For the next question, Anuj, who's on with us live, who would like to know, and I'm not sure I agree with the premise of the question, but you can take care of that, I think. Does everything in nature occur in pairs? Are trios rare, or is the possibility of pairs, trios, or singular objects just random chance, or have equal possibilities?
So it's a general question, and sort of depends on what domain of nature you're talking about. There is if we start at the microscopic level of subatomic particles, there's no particular preference for any number of any multiplicity of particles. There's a duality, of course, between matter and antimatter, physical entities with opposite quantum properties. So in that sense, there's a pairing in a symmetric sense. But as far as do particles tend to inhabit in multiples of 2 as opposed to any other multiple, I would say no, there's no sense of that. If we get up to larger objects, where maybe now talking about the realm of planets and so on, and stars, then we know that single isolated stars are actually rare. So our sun is a minority object in a sense. Binary stars are quite common, so there's definitely a tendency in astronomy, in the way that stars form, for binaries to be favored. Not more binaries than single stars, but a substantial fraction of all stars are in binary systems, and a much smaller fraction in triple or higher multiplicities. So astronomy does have a slight inclination towards binary systems. That also is true of galaxies. There are galaxies that are in binary orbits and pairs of galaxies, and astronomers have found hundreds of examples of those. But there are also situations where there are 3 galaxies or 4 or 5, and they're gravitationally bound. So general answer to the question is no. There's no strong preference to duality or pairing on any physical scale. Ready for the next question?
All right. The next question is from Keith, who has a question about black holes. Keith is on with us live and would like to know, if you had a tethered probe and sent it into the event horizon of a black hole and then boosted a signal, would it still not get out because no information leaves a black hole? How does that work if you were physically connected?
Right. So there's an immediate practical problem just in having a physical tether, because if you create a physical object like a tether, a rope, or an incredibly strong carbon nanotube cable, so the strongest material you can imagine, it's going to be suffering enormous tidal forces as the object that it's tethered to falls into the black hole. So at the moment, we know of no physical material we could make that could survive being disrupted by the gravitational stretching force of falling into a black hole. So I think that's the first problem, that it's just very unlikely that a physical object could survive intact. Even let's say it could, the question then becomes, is it a means of transmitting information out of the black hole if one end of the tether is past the event horizon and the tether extends through the event horizon to our side of the black hole? In principle, yes, but actually in practice, no, because the event horizon is still a barrier, and so the point at which the tether essentially is lost in the event horizon also corresponds to a location where the redshift of information from that tether is infinite. And so reflected light or electromagnetic waves or whatever signal you might want to get out from that part of the tether is unavailable to us. And that's essentially why the black hole event horizon is a boundary to information. So according to black hole theory, no, we still wouldn't get any information from that tether or via that tether, even if the tether could survive that physical situation. Ready for the next question?
All right, thank you, Chris. The next question is from Michelle, who sent an email, and Michelle would like to know, how do astronomers or scientists address advances in technology that occur while instruments like the Giant Magellan Telescope are being built? So, for example, the glass mirrors. How do we deal with advances in technology?
Right. So for the mirrors, it's not usually a problem because advances in mirror-making technology actually happen quite slowly. The 2 major methods by which the big telescopes of the world are being made involve sort of mosaics of small hexagonal segments. That was the Keck model that's being used for the large California telescope that's maybe going to be located in Hawaii if they get permission. And the European project, which will also be made of a mosaic of segments. The method being used in Arizona for our Giant Magellan telescope is huge, 8.4 meter mirrors, 6 of them in a common mount. And those methods really haven't changed. Those have been the methods that those two groups have been using in a friendly and competitive way for a couple of decades. What evolves on a faster timescale is the instruments. So telescopes need to use the most current technology for their instruments. Again, it's not usually the optics, because optics is a mature field, and the way to design a spectrograph or make a wide field imager, those are well-established techniques. They're decades old, and they don't change. But the actual guts, the detector, the final surface that senses the photons, those come out of research labs. They're always trying to improve them. And so that's where you have to be nimble and try and get the most recent advance. With the ground-based telescope, that's still pretty easy, because the telescope is built, it gathers light, it has a spectrograph, and you're just talking about the last step, the surface or the little box that's cryogenically cooled where the CCD or other detector is, and you can replace that detector fairly easily. The problem comes not with the ground-based telescopes, but with space instruments like the Hubble and the James Webb. There, the problem is the timeline of development. To be part of a space mission, NASA essentially, or other space agencies, insist that the technology not evolve right up to the point of launch. So while you might think, oh, we've got our facility and we can just do what the ground-based people do, just swap out the detector at the last minute to get the very best one straight out of the research lab, you can't do that, because the detectors are built into packages. They're launched and have to go through extreme physical stresses of rocket launch into Earth orbit. And NASA, to ensure that there's no failure, insists that these detector packages be sealed and delivered to them several years ahead of launch. And that means that the R&D to produce that detector package and convince NASA it has enough sensitivity and stability and reliability, that's another few years. So with the NASA mission or a space mission, you're almost always using a detector technology that's 6 to 8 years old or away from state of the art. That's not always a problem, because even 6 or 8 years ago, the detectors are pretty darn good, but they're obviously not as good as the ones being made right now. And so I would say it's in space astronomy where this sort of lockdown of the technology ahead of launch causes the biggest concern. Ready for the next question?
All right, thank you, Chris. I believe this is going to be our last question for the session today. And that question is from Andrea De Carvalho, who would like to know, how do we know that glass rains down on planets that are so far away from us?
Right. This is alluding to sort of evocative news stories about the extreme conditions of some exoplanets or some distant planetary situations. So the short answer is we don't know for sure, because these are based on modeling the physical conditions. But spectroscopy is good enough to tell us what the chemical and molecular situations in a planetary atmosphere are. These measurements are also good enough to tell us what the temperature is and the density of the atmosphere, most likely, based on a model. And so if you know the chemical composition and the atmospheric thickness and depth and temperature and density, then you have some fair reliability to say that these particular molecular species, including glassy materials, could form globules or nucleate or condense in that atmosphere, and if the atmosphere is cool enough, rain down onto the surface. So you can see the chain of logic. It's based on a fair amount of inference, but it's based on direct measurement of chemistry and physical conditions. And it leads to that evocative type of statement. So it's one of the fun things about exoplanets, that we can actually speculate about these bizarre physical environments. Thanks for all your questions this week. They were great questions, as always. And thanks to Michael and Alexander and Matthew for facilitating the session. And we'll be back with you in a couple of weeks.